Welcome everyone. Today's lesson is entitled Linear Functions Day 1. Linear functions represent the first among many families of functions that we will be investigating over the course of our curriculum, and it's probably a good one for us to start on, as I'm assuming that most, if not all of this lesson will be a review for you. So why don't we go ahead and dive right in. There are a lot of little blanks to sort of fill in over the course of the front side. And before I do forget, you will actually need a ruler and protractor for this lesson if you can grab one. If you absolutely can't, you're not going to stress about it. We'll kind of work our way around it a little bit if need be. But a ruler and protractor would help. I have a little quick hands-on activity on the back side of this sheet to get us thinking of a particular concept. All right, so when we talk about linear functions, one of the first and most important concepts relates to the idea of slope. And so if you remember slope formula, if we're given 2 points on the line, and slope is denoted with the letter m, and so slope is a ratio of change in y over change in x. So that's y2 minus y1 over x2 minus x1, of course. So that is our slope formula given any 2 points on the line. And sort of the verbiage that goes with slope formula, sometimes you hear it expressed as, and in fact I'm going to kind of put quotes around it, the rise over run. So the rise of the line over the run of the line. The rise represents the change in y on the coordinate plane, and the run of the line represents the horizontal change, or the difference of the x's. So rise over run, change in y over change in x. Now in graphical terms, the slope measures the steepness of the line. So if we have any two slopes and we're comparing them, we can compare how steep one is compared to the other. In application problems, the slope represents really the constant rate of change, but I'm going to be a little more generic with it. So just the rate of change. And we'll be dealing a lot with the concept of rate of change in this curriculum as well. So we've got that, and then it looks like the next four kind of go together here. Increasing lines, decreasing lines, horizontals, and verticals. So just refreshing your memory on the nature of the slope in each circumstance here. So I'm going to go ahead and read it, maybe draw it, and then we'll fill in the blank, of course. So it says if the line is increasing from left to right, so that would be looking like this, and I would just draw that quickly on your paper kind of like I did. So if it is increasing from left to right, then the slope of the line is always positive. So an inclining line, like that right there, positive slope. If we have a declining line, meaning the line is decreasing from left to right, and of course that would look like this. And if it is a declining line, then the slope is negative. Okay. And if the line is horizontal, so of course that would look like this, then the slope is 0. And that makes pretty good sense for a couple reasons. Number one, if graphically the slope measures the steepness of the line, then a horizontal line has 0 steepness, and so the slope would be 0. And what's interesting, just graphically, if I have a horizontal line, what I know to be the case is that if with any 2 points, the y values would be the same. And if the y values are the same, and I go to my slope formula, and if I look at the numerator, if I have 2 y values that are the same and I subtract them, then I'm getting 0 as a numerator over a non-zero value as a denominator. So 0 divided by that number will give us 0, of course. And then lastly, if the line is vertical, so let's draw that in place here, then the slope is considered undefined. And again, you've probably seen that idea before. But if I referred it to what I've written on the board already, as slope being a measure of steepness, I would consider a vertical line having infinite steepness. And so there's no finite number that I'm going to be able to define for that slope. But also, if I think about it mathematically, what I know to be the case on a vertical line on the coordinate plane is that for any 2 points, the x-coordinate would be the same. And if the x-coordinate is the same here and here, well, I go to my slope formula, and I would have 2 values where the x-coordinates are the same, and if I take those 2 x values and subtract them, then I'm going to get 0 in the denominator. And if I get 0 in the denominator, of course, anything divided by 0 is undefined. So I hope just in terms of the conceptual aspects of it, these 2 values make sense to you. And then, of course, mathematically, using the formula, we would, of course, get those values as well. Now, I think I've already alluded to these 2 pieces here. These are a little more obscure for the types of lines that we're going to continue to see, but we'll put them in place nonetheless. So the equation of a horizontal line, and actually, as I said, I already alluded to the fact, what I know to be the case about a horizontal line is that all of the y-coordinates are the same number. And so, very simply, that is going to represent the equation. So the y value is equal to some value. Typically with this, you call it b, and we'll see why in just a little bit here. So y is equal to a constant, whatever that constant may be. Whereas the equation of a vertical line, again, what I've illustrated here is on the coordinate plane, if I have a vertical line, what I know to be the case is that all of the x values are the same. And so to represent that, it's very simply x equals that constant, whatever it may be. And typically you see that with an a. As I said, these 2 scenarios are a little more obscure. We're not going to spend a ton of time on them. What we will spend a lot of time on is this, so throw a little asterisk right there. And as I said, this should look very familiar to you. So slope-intercept form of a linear equation, meaning within the form of the equation, it denotes the slope, and it denotes the y-intercept. That's what the intercept stands for there. And of course, you've seen this potentially as y equals mx plus b. Slope is the m, y-intercept is the b. And just because we are really talking about it as a function, remember f of x is an alternative way to talk about y. So f of x equals mx plus b. Should be comfortable with your generic y or your function notation f of x. And as I already said, m represents the slope, and b represents the y-intercept. Just be careful on that, not the x-intercept. All right, and as I said, I went through that rather fast, but from my perspective, you've seen all of that before. All right, let's move on to my next board here. We'll just do some equations, get us thinking about it. Now, the one thing with this particular lesson that I am skipping over, just for your information, is what's called the point-slope form of an equation. And potentially you'll get to that maybe at the next level and the next level when you do a little more with this type of stuff. For our purposes, the slope-intercept form is really all we need, and so I'm really going to highlight that piece with all of these problems that we see. All right, so let's get into example 1. It says write the equation for the line with a slope of 3 and through the point -2 and 4. All right, easy enough. When I see slope of 3, and by the way, you don't have to label it, but slope of 3, that's going to be our m value. The point is -2, 4, and that is one of an infinite number of points on the line. So as I think about my y equals mx plus b, which is exactly what I'm going to do right here, I'm going to use what I have to solve for potentially what I need. Now I know I need the slope and I need the y-intercept to represent all of the x's and y's on the graph of the line. In this case, I have a slope to work with, so I'm going to go ahead and put in 3 directly there. And I have a point on the line. So the idea being, if this is a point on the line, then it makes the equation true. And so I can use the 4 for y and the -2 for x in order to solve for the piece that I'm missing, which of course is the y-intercept. And so I'm going to go ahead and just solve this quickly. This would be -6, and I'll add 6 to both sides. And if I'm jumping the gun a little bit, sorry about that. You can ask about it, and I can walk you through in a little better detail. But it looks like we get a b value of 10. So as a result, now that I have a numerical value for the slope, a numerical value for the y-intercept, we're ready to write our equation for all of the points on the line. And we would get something like this. And you don't have to do this if you don't want. I just want to refresh your memory. Graphing equations. I'm not even going to get like a tick marks going or anything like that. But just recall what this represents. So this would be a y-intercept of 10. So up here, that's where it crosses the y-axis. And as a slope of 3, remember slope is always a ratio of rise over run. So this would be a 3/1 ratio. So it would be like up 3/1, could put a point. Up 3/1, put a point. And you could see I could do that an infinite number of times, and it would always be on the line right there that I would draw. And as a matter of fact, you know, up 3 and right 1 is the same as down 3 and left 1. Something like that and so forth. And anyway, again, you've been doing this a lot in your Algebra 1 class, so just something like that. Said it's not necessary for our purposes here, just wanted to refresh. Let's move on to example 2. Write the equation for the line that passes through these 2 points here. And you could, doesn't have to be first point, second point, but I'm going to go ahead and label it as such. So x1 and y1 right there, x2 and y2 right there. And again, what I'm thinking in my head is I need the slope and I need the y-intercept. I have neither in this particular case. And so my first order of business is to find the slope. That comes first. And so we're going to do our little rise over run here. And so just kind of looking at this, remember this, y2 minus y1 on top, so -1 minus 2 in the numerator. Run on the bottom, so this would be x2 minus x1, so 2 minus -4 in the denominator. And this, of course, just gives me -3 over +6. And so we could make the case that the slope is -1/2. Now, just thinking about this graphically, what does that mean, everybody? Is it an inclining line or declining line? And remember, we talked about as soon as you see a numerical value for the slope that is negative, it would be a declining line. Maybe we'll do the same thing and kind of draw it at the end after we get the equation. All right, but anyway, now once I have the slope, I'm back to the same scenario of example 1, where I go ahead and throw the -1/2 in for m. Now, either of these points would work, of course, because they're both points on the line. So either one would make the equation true. It is entirely up to you which one you want to put in. This is just the one that jumps out at me. And so I'm going to go ahead and put in the 2 for the y. X is -4. Add the b. And, of course, when I do the multiplication here, -1/2 times -4 is 2. And to get the b by itself, I'd subtract 2 on both sides. So I'm getting a b value of 0. And so as a result, we get y equals -1/2 x. Obviously, you don't have to put the +0, but if you did, so be it. Okay, awesome. And again, just a quick refresher. I don't want to overplay my hand here by any way. But first of all, y-intercept would be 0. So it would go right through the origin. And when I see a negative slope, I think of it as kind of down 1, right 2. So down 1, right 2, down 1, right 2. Or I could think of this as up 1, left 2. Either way works, and you can see no matter what, I'll certainly be on the line. And so my line looks something like that. Perfect. Let's get into the next scenario. So what happens when I have any two, I don't want to give too much away with this, but lines that have the same slope, so the same rise over run. So if I was to draw kind of a line here, think of the rise over run, and then try to draw a line with that same rise over run, probably would look like this, because same rise over run. And I think I probably gave it away, but that's all right. So lines with the same slope, of course, are parallel. And you can see that leads nicely into example 3. Write the equation for the line through this, 3, 2, and parallel to the line defined by this right here. All right, very nicely done. And I might go ahead and draw this out just for us to get an idea. I'm going to erase this. This is kind of unnecessary. So let's see what's going on here. So the line is going to go through 3, 2, and again, I'm not going to be so specific with it. It's about there, give or take. And through or parallel to this line right here, meaning the y-intercept of the given line is 8, and it's going down 1, right 1, so kind of like this. So we want the line parallel to this and going through this right here. So we want, I guess I'll dot it or something just so you can see what we're looking for. So I want that dotted line right there. That's kind of our scenario. All right, well, let's see what we've got. So everybody, if you would, write a little y equals mx plus b for me. And do I have the slope of this dotted line right here? Well, yeah, absolutely. Because in the equation for the given line, the slope happened to have been -1, right? So -1x plus 8. So in this particular case, the slope would be -1. Down 1, right 1, down 1, right 1, et cetera, et cetera. And of course, I have an x and a y on the line that we need, so it has to go through that point. And if it has to go through that point, it makes the equation true. And so I'm going to throw 2 in for y, 3 in for x, solve for b, and I get -1 times 3, which is -3. Add the 3 to both sides, and it shouldn't come as a major surprise here that I get a b value of 5. Remember the way I drew it, here's a b value of 8. You know, here's the y-intercept that I drew initially, and obviously it's positive and it's below 8, so this certainly seems reasonable to me. And so as a result, we've got -1x plus 5. All right? So parallel lines have the same slope. Now, if you would, and I'll try not to take a ton of time with it, it's a cool one to look at, but I don't know. It's not mind-blowing per se. So let's talk about now the slopes of perpendicular lines, and I figured we would try to draw this out as best we could. So if you get a chance, ruler and protractor would be very nice here. And here's what I'm going to ask you to do. And if not, you know, again, so be it. Maybe you can just kind of do it as best you can, freeform, and, you know, maybe you'll see the concept anyway. I mean, obviously, that's what I'm going to have to do here. So anyway, here's what I'm thinking. If you would, give me an x-axis straight across. Use your ruler as best you can. All right, now what I want you to do is basically locate the middle of your x-axis, give or take, and we'll call that the origin right there. Okay. Now, if you do have a protractor, let's break that on out. Put your protractor on what will be the origin, and if you can mark off 90 degrees on your protractor, and just put a point there to mark off 90 degrees. So we are creating a right angle, obviously with our x-axis, in order to make the y-axis. And so when you have that 90 degrees marked off, if you would, go ahead and draw your y-axis in play with your ruler. Okay. Now, we're going to do 2 lines going through the origin, and we're going to be very careful about the slope. And here's how you're going to do it. I'll slow down just a touch. You're going to grab your ruler. From the origin, you are going to go a certain number of units to the right. You're going to decide what works best for you. So a certain number of units to the right. And you're going to just put a little point, not a big one, just a little point right there. And that value we're going to call A. So I'm going to put a little A right here. Now off to the side, just off to the side here, can you write for yourself what A is equal to? Because you're going to come back to A in just a little bit. So if you're like, okay, this is 2 centimeters, just make a little note that A is 2 centimeters right there. All right? Cool. So whatever A is, you have that number written down just so you don't forget it. Okay, now what I want you to do is grab your protractor And from that particular point, can you mark off another 90 degrees going up? So again, just mark off 90 degrees, just like that. And now through that point, I want you to measure a different distance. So for example, like if I did 2 centimeters here, I'm going to do something different here, whatever it may be. So whatever you want, does not matter to me. Go a certain number of units up and through that point, and put a bigger point right there. And that we're going to call B. So whatever number you decide does not matter to me. That is B units going up. And make a little note just off to the side, because you're going to see this in just a minute again, what your B value is. And here's what you're going to do. We have 2 points on a line, the origin. And by the way, probably not a bad idea. Can you put a little 0, 0 right there for the origin? And let's do this. Let's label this point. Now that I'm looking at it, you went over A units, you went up B units. So everybody, no matter what the numbers are, label that A comma B. And grab your ruler and draw a line through those 2 points. Okay. Excellent. Let's do our construction. Let's finish the construction part of this. And then we'll do the slopes themselves. All right, so line 2. Here's how it's going to work, everybody. Now in this particular case, you're going to start at the origin. Again, you're going to grab your ruler. And whatever your A value was, whatever number you made that, what I want you to do is measure that going up on the y-axis. So for example, if I went 2 centimeters for my A, okay, now I'm going to go up that 2 centimeters, and I'm going to go ahead and just put a point right there. So from the origin to that point is A. And then if you can kind of move your paper a little bit here, you're going to put your protractor on this point, and you're going to mark off 90 degrees going to the left. So just 90 degrees going to the left as best you can. And now from here, through your point, you're going to go B units and mark another point. So again, if I said, oh, you know what, my B value is 3 centimeters, okay, that's great. Now I'm going to go 3 centimeters through that point and do something like that right there, and this would be B. Okay, and then put a point right at the end. Awesome. Okay, now I'm going to create my second line. That goes through the origin and this point right there. Everybody draw with your ruler as best you can. Looking good. Now I've got 2 lines. I'm going to label one more point, and then we're going to do some slopes. Okay, first order of business. If I wanted the ordered pair here, I actually would go horizontal and vertical, right? I went left B units. So if I go left on the coordinate plane, that would be negative B, and then up A. So I hope you would agree with me that this would be negative B comma A right there. Great. Hey, everybody, grab that protractor and measure the angle in between your 2 lines. So measure the angle right in here, and hopefully, if all worked out, you should see that right in there is a right angle, meaning we constructed, as best as possible under the circumstances, 2 perpendicular lines. Awesome. Now let's look at the slopes. So rise over run, or y2 minus y1 over x2 minus x1. So let's do this. I'm going to do m with a subscript of 1, so the slope of our first line. And if I do y2 minus y1 over x2 minus x1, that would be b minus 0 over a minus 0, which of course would be b over a. Okay, that looks great. Now everybody, if you could, let's do m with a subscript of 2, so the slope of the second line. Same idea, y2 minus y1 over x2 minus x1. So in this case, it would be a minus 0 over negative b minus 0. And when I, of course, do that, I get a over negative b. So to make a rather long story short, we have two perpendicular lines. Look at the slopes, and as the question suggests, what is the relationship of the slopes of perpendicular lines? And as mentioned, I believe you've seen this before, but this illustrates this nicely, I believe. You can see, first of all, they are opposites. Think of this as a negative slope. This one's a positive slope. And they are also reciprocals. This is A over B. This is B over A. And so that's what you're going to write. They are what are called opposite reciprocals. One positive, one negative, and they are reciprocals of one another. Now this works for every two perpendicular lines except, let's go with the question, is there a situation where this relationship does not hold? Yeah, I'm afraid there's one. So there's only one situation where if we drew two perpendicular lines on the coordinate plane, we would not see opposite reciprocals. Can anyone maybe think about what that might be? How about a horizontal line where the slope is 0 and a vertical line where the slope is undefined? That's the only situation where you wouldn't see numerically the opposite reciprocal relationship. Okay, great. Let's get into example 4 then, using this situation. And again, I hope you've found this to be at least intriguing, if not, as I said, earth-shattering. Okay, example 4. Write the equation for the line through, so it's going to go through this point, and perpendicular to this line right here. So this is in what's called general form. We've got our x, we've got our y, our constant equal to 0. That's all well and good, but you know what? It's not helpful just yet. So what we need to do is put this into slope-intercept form to start. So everybody, subtract the x. Add the 6. So I would get negative x plus 6 on this side. We're going to put it into y equals mx plus b, of course. I'm going to divide everything by 2, and I mean everything by 2. So when I divide by 2, I get negative 1 over 2. So that's negative 1/2 x. And yes, I divide everything on the right side by 2, so this would be plus 3. So this is the given line. And again, I like to be visual with everything that I do, if at all possible. So what I'm seeing is it has to go through 2, negative 3. So here is 2, negative 3 right here, give or take. If I was to graph this line with a y-intercept of 3 and down 1 over 2, probably looks something like that. So we need a line that goes through this point and is perpendicular to this line right here. So I'm going to dot it, but I'm hoping you would see probably something like that right there. So perpendicular line through this point and perpendicular again to that line right there. All right. Well, everybody, please put y equals mx plus b. Now, we have the slope of this line. We just have to kind of figure it out, and it comes from the slope of the perpendicular line. So if the slope of this line right here is negative 1 over 2, then the slope of the line we need is positive 2 over 1. Opposite, reciprocal. So the slope is 2. And of course, x is 2, y is negative 3, and we solve for b just like we've done. So everyone, 2 times 2 is the 4. Subtract that 4 on over. And again, just looking, does that make pretty good sense? Does this look to be down at negative 7? Sure, why not? So y equals 2x minus 7. Okay, very good. Let's move on to the next. Example 5, write the equation of the line perpendicular to x equals 3 and passing through 1, negative 4. What you may want to remind yourself with this particular problem, when you see x equals a constant, that is a vertical line. So a vertical line when x is 3, and then passing through that point. Let's see it visually. So x equals 3, so I would go over on the x-axis, 1, 2, 3, and it would be a vertical line. And again, if you were to pick any point on this vertical line, guess what the x-coordinate would be? 3. And that's why it's defined that particular way. All right, and it passes through 1, negative 4, so something like that. And we want it perpendicular through that vertical line. So obviously a line that's perpendicular to a vertical line is a horizontal line. Well, let's keep this one simple. What do we know about a horizontal line? Well, I know all the y-coordinates are the same. So if I'm looking for a perpendicular line to a vertical line, then it's got to be horizontal. And I know the y-coordinates are the same. Well, what are the y-coordinates on that line? Negative 4. And by the way, just to relate it very, very quickly to slope-intercept form, remember a horizontal line has a slope of 0. So if I'm really kind of thinking mx plus b, isn't this obviously the same as that? Do I need to write the 0x? No, of course not. But it fits, obviously. Here's your slope of 0, y-intercept of negative 4. Oh yeah, by the way, all of the points, all of the y-coordinates on that line would be negative 4. All right, let's do one application to kind of wrap this on up here. So just pretty straightforward, a linear relationship. Looks like linear growth, as a matter of fact. All right, let's see. A tree was planted on the property here in 1970. In 1975,